Imagine a mysterious object, unlike anything seen before, racing through our solar system at breakneck speed. It lacked a comet's glowing tail, yet accelerated as if pushed by an invisible force. This was no sci-fi tale. This was the real discovery of Oumuamua in late 2017. Astronomers in Hawaii spotted it, naming it Oumuamua, meaning messenger from afar. For the first time, we witnessed an object from another star system passing through ours. Theorized for decades, interstellar visitors were suddenly real. Oumuamua proved our solar system is open to cosmic wanderers. Its arrival raised urgent questions. What was it? Where did it come from? Could it even be artificial? The world watched as scientists raced to solve the mystery. Join us as we unravel the secrets of Oumuamua, the strangest visitor in modern astronomy. Oumuamua's name, chosen in Hawaii, means a messenger from afar arriving first. The name captured the wonder and curiosity sparked by its discovery. This wasn't just another asteroid, it was the first known interstellar object to visit our solar system. Oumuamua became a symbol of the unknown, igniting global fascination. Its arrival reminded us of the vast mysteries beyond Earth. The name itself is a tribute to the cosmic journey it represents. Scientists and the public alike were captivated by this celestial messenger. Next, we'll explore the scientific observations and theories that make Oumuamua so unique. On an ordinary night in October 2017, the Pan-STARRS 1 telescope in Hawaii detected a faint, fast-moving object. At first, astronomers thought it was a typical asteroid or comet, but its path wasn't elliptical, it was hyperbolic, meaning it wasn't bound to our sun. This was the first concrete evidence of an interstellar object entering our solar system. The discovery electrified the scientific community. Pan-STARRS 1's advanced imaging made this breakthrough possible. Oumuamua's detection opened a new chapter in our understanding of the cosmos. Suddenly, the idea of interstellar visitors was no longer just theory. The object's unique trajectory set it apart from anything seen before. The hunt to understand Oumuamua had begun. Oumuamua's hyperbolic trajectory confirmed its interstellar origin. It briefly swung by the sun, then sped out of our solar system forever. By the time it was spotted, it was already leaving at high speed. Scientists had only a short window to study this cosmic visitor. The discovery proved our solar system is part of a vast interconnected universe. Telescopes worldwide scrambled to gather data before it vanished. The race was on to unlock the secrets of this rare interstellar traveler. Oumuamua's fleeting visit changed our view of the cosmos. Observing Oumuamua was a race against time. Its incredible speed and faintness made it a difficult target. Only a few hundred meters long, it reflected little sunlight and quickly faded from view. Astronomers used sensitive instruments and global collaboration to track it. Every bit of data was precious, offering clues about its nature. The international effort highlighted the power of teamwork in astronomy. Scientists worked tirelessly to capture as much information as possible. Oumuamua's brief appearance tested the limits of our technology and curiosity. Oumuamua's shape was unlike anything seen before. Astronomers analyzed its changing brightness to infer its form. The data revealed an extremely elongated object, like a cosmic cigar or needle. Estimates suggested it was 5 to 10 times longer than it was wide. This bizarre shape set it apart from typical asteroids and comets. Scientists debated how such a form could arise: collision, fragmentation, or something unknown. The elongated shape became a central mystery. Oumuamua challenged our understanding of how objects form in space. Oumuamua wasn't just oddly shaped, it tumbled chaotically through space. Its unpredictable rotation suggested a violent past, perhaps a collision. The tumbling motion was detected through erratic brightness changes. This complex spin indicated a solid, cohesive structure. Few forces in interstellar space could alter its motion, so it likely tumbled for eons. The combination of shape and rotation deepened the mystery. Oumuamua was no ordinary wanderer. Each discovery raised more questions about its origin and journey. Spectral analysis revealed Oumuamua's reddish hue. This color suggested exposure to cosmic radiation over millions of years. Such radiation alters surface chemistry, creating a red tint. The hue hinted at complex organic molecules, tholins, on its surface. Tholins are found on other radiation-bathed objects like Pluto. Oumuamua's color supported its interstellar origin. It may have carried the raw ingredients for life across the galaxy. The surface told a story of a long, lonely journey through space. As Oumuamua left the sun, it accelerated in a way gravity alone couldn't explain. Normally, comets accelerate by outgassing, but Oumuamua showed no such activity. Sensitive telescopes found no gas or dust around it. The cause of its acceleration remains a mystery. This anomaly fueled wild speculation. Was it a new natural phenomenon, or something artificial? The unexplained acceleration became the object's most perplexing trait. Scientists debated every possibility, from physics to alien technology. Oumuamua's behavior defied easy answers. The mystery only deepened as it sped away into the void. Its legacy, a cosmic puzzle that continues to challenge our imagination. Faced with the enigma of Oumuamua's unexpected acceleration, astronomers initially turned to the familiar to explain the unfamiliar. Could it be that our interstellar visitor was, at its core, a comet after all, albeit one with some rather unusual properties? The idea was that Oumuamua might be outgassing, just like comets in our solar system, but doing so in a way that eluded our telescopes. Perhaps the material being ejected was not the usual mix of dust and ice that creates a visible coma and tail, but something more elusive, something invisible to our instruments. One suggestion was that Oumuamua might be releasing pure water vapor as it was warmed by the sun. Water vapor is transparent and wouldn't be easily detected by telescopes, yet it could still provide a small thrust as it escapes the object's surface. This hypothesis seemed plausible at first glance, offering a way to explain the acceleration without resorting to entirely new physics or exotic materials. However, the invisible comet hypothesis faced a significant hurdle. If Oumuamua were indeed venting gas, even if invisible, this outgassing should have had a noticeable effect on its rotation. Jets of gas escaping from an irregularly shaped object like Oumuamua would create uneven forces, causing it to spin faster, slower, or even tumble more erratically. Yet observations showed that Oumuamua's chaotic tumbling remained remarkably consistent, with no evidence of the spin variations expected from outgassing. Moreover, while water vapor outgassing could potentially explain a small acceleration, the magnitude of Oumuamua's speed boost was difficult to reconcile with this mechanism alone. Calculations showed that an enormous amount of water vapor would need to be released to account for the observed acceleration, far more than what would be expected from a typical comet, even an unusually dry one. While the invisible comet hypothesis couldn't be completely ruled out, it became increasingly clear that a more nuanced explanation might be needed to fully account for Oumuamua's peculiar behavior. With the invisible comet scenario facing challenges, some scientists ventured further into the realm of the unusual, proposing that Oumuamua might be composed of something far more exotic than the typical water ice found in comets. Their attention turned to ices that could exist in the frigid depths of interstellar space, far from the warmth of any star ices that could potentially explain both the acceleration and the lack of a visible coma. One intriguing possibility was that Oumuamua was a hydrogen iceberg, a chunk of pure frozen molecular hydrogen that had coalesced in the extreme cold of a giant molecular cloud. Hydrogen is the most abundant element in the universe, and under the right conditions, it can freeze into a solid state. A hydrogen iceberg, warmed by the sun, could release hydrogen gas that would be invisible to telescopes, but still capable of providing a gentle thrust. While the hydrogen iceberg hypothesis was ingenious, it too faced obstacles. Calculations showed that a hydrogen iceberg traveling through interstellar space for millions or even billions of years would be constantly bombarded by cosmic rays and starlight. This relentless radiation would gradually erode the ice, causing it to sublimate and eventually disappear long before it could reach our solar system. In essence, a hydrogen iceberg would have a limited lifespan in the harsh environment of interstellar space, making it unlikely that Oumuamua, having journeyed from another star system, could be made of such fragile material. Another exotic ice hypothesis emerged, suggesting that Oumuamua might be a fragment of a Pluto-like exoplanet, a shard of frozen nitrogen chipped off the surface of a distant world. Nitrogen ice could survive the interstellar journey, and importantly, it could sublimate in a way that produced invisible gas, potentially explaining the lack of a coma. This hypothesis also offered a potential explanation for Oumuamua's elongated shape, suggesting that it might have started as a more typical chunky object, but was gradually sculpted into a sliver by the uneven sublimation of nitrogen ice. While intriguing, the nitrogen ice hypothesis still relied on a specific set of circumstances, a Pluto-like exoplanet suffering an impact and ejecting a nitrogen-rich fragment in our direction, making it a statistically less likely, though still possible, explanation. As scientists grappled with the unusual properties of Oumuamua, a more radical explanation emerged from the fringes of mainstream astronomy. The possibility that this enigmatic visitor was not a natural object at all, but rather a piece of alien technology. This audacious hypothesis, championed by Harvard astronomer Avi Loeb, ignited a firestorm of debate and captured the public's imagination. Loeb and his colleagues argued that Oumuamua's peculiar combination of characteristics, its elongated shape, its unexpected acceleration, and the lack of a visible coma, could be explained if it were an artificial light sail, a thin, reflective craft designed to harness the momentum of sunlight for propulsion. Just as a sailboat uses the wind to move across the water, a light sail uses the pressure of photons from a star to accelerate through space. The light sail hypothesis was based on the idea that an advanced extraterrestrial civilization might develop such technology for interstellar travel. A thin, reflective sail, unburdened by the need for fuel, could theoretically reach incredible speeds, allowing a spacecraft to traverse the vast distances between stars. Loeb argued that Oumuamua's trajectory and acceleration were consistent with what might be expected from a light sail, and its unusual shape could be explained if it were a broken fragment of a larger craft. While the alien light sail hypothesis was undeniably intriguing, it was met with skepticism from the majority of the scientific community. Critics pointed out that all of Oumuamua's observed properties could potentially be explained by natural phenomena, even if those phenomena were unusual or poorly understood. They argued that invoking alien technology was a premature leap, especially given the lack of any direct evidence to support such a claim. Despite the controversy, the alien light sail hypothesis served as a potent reminder that our understanding of the universe is constantly evolving, and we should remain open to unexpected possibilities, even those that challenge our current understanding of physics and technology. Just when the mystery of Oumuamua's acceleration seemed destined to remain unsolved, a surprisingly simple and elegant explanation emerged, one that didn't require exotic ices, alien technology, or new laws of physics. In 2023, researchers Jennifer Bergner and Daryl Seligman proposed that Oumuamua might be a dark comet, an object composed mostly of water ice but with a crucial twist, a significant amount of trapped molecular hydrogen. Their hypothesis was based on the idea that as comets travel through interstellar space, they are constantly bombarded by cosmic rays. This radiation can penetrate deep into the ice, breaking down water molecules and creating pockets of trapped hydrogen gas. When warmed by a star, this trapped hydrogen is released, acting like a subtle but persistent thruster. Crucially, because pure hydrogen gas is transparent, it wouldn't produce the visible coma or tail we typically associate with comets. The dark comet hypothesis elegantly explained Oumuamua's peculiar acceleration without requiring any exotic materials or extraordinary events. It suggested that Oumuamua was not entirely dissimilar to comets in our own solar system. It was simply a comet that had been traveling through interstellar space for so long that its composition and behavior had been altered in subtle but significant ways. The dark comet explanation has gained significant traction within the scientific community, with many astronomers now considering it the most plausible explanation for Oumuamua's mysteries. While some questions remain, and further observations of similar interstellar objects will be needed to confirm this hypothesis, the dark comet theory has provided a satisfyingly parsimonious solution to one of the most intriguing astronomical puzzles in recent memory. It serves as a reminder that sometimes the most straightforward explanations, based on known physics and plausible processes, can unravel even the most perplexing cosmic enigmas. The scientific community, always striving for elegant solutions grounded in established principles, found a sense of resolution in the dark comet theory. It offered a framework to understand Oumuamua's eccentricities without resorting to entirely new physics or invoking extraterrestrial intervention. While the alien light sail hypothesis had certainly captured headlines and sparked public imagination, the dark comet explanation resonated more deeply with those seeking answers within the known laws of nature. The beauty of the dark comet theory lay in its simplicity. It postulated that Oumuamua was, at its core, not fundamentally different from comets found within our own solar system. The key difference lay in its long journey through the harsh radiation environment of interstellar space. Cosmic rays, those relentless streams of high-energy particles, had, over eons, altered the very composition of the comet's ice. This bombardment had created pockets of trapped molecular hydrogen, a substance that, when warmed by the sun, could provide the gentle but persistent push observed as Oumuamua sped away. The theory also neatly addressed the lack of a visible coma, the telltale sign of outgassing that we typically associate with comets. Because pure hydrogen gas is transparent, its release from Oumuamua would have been invisible to our telescopes, explaining why we detected the acceleration but not the expected plume of gas and dust. This seemingly minor detail easily overlooked in other hypotheses, was elegantly accounted for by the dark comet explanation. While the dark comet theory has gained widespread acceptance, it's important to remember that science is a process of continuous refinement. Future observations of similar interstellar objects will be crucial in confirming or challenging this model. Each new visitor from the depths of space presents an opportunity to test our understanding and refine our theories, pushing the boundaries of our knowledge about the cosmos. Just as the dust was settling around the various theories attempting to explain Oumuamua, a second interstellar visitor arrived on our cosmic doorstep, further enriching the story and deepening the intrigue. In August 2019, Gennady Borisov, an amateur astronomer in Crimea, discovered a cometary object on a clearly hyperbolic trajectory, marking it as another traveler from beyond our solar system. This new object, officially designated 2I/Borisov, provided a fascinating counterpoint to Oumuamua, further highlighting just how unusual the first interstellar visitor had been. Unlike its enigmatic predecessor, Borisov presented itself as a rather typical comet, readily identifiable by its visible coma and tail, classic signs of outgassing as the sun warmed its icy surface. Its composition, as deduced by spectroscopic analysis, also appeared to be consistent with comets found within our own solar system, suggesting that the processes that form and eject these icy bodies are likely universal. The arrival of Borisov, behaving exactly as astronomers would expect from an interstellar comet, underscored just how peculiar Oumuamua was. If Borisov represented the norm, a typical example of the kind of icy wanderers ejected from planetary systems, then Oumuamua, with its bizarre shape, lack of coma and anomalous acceleration, stood out as a true outlier, a cosmic oddity that continued to intrigue and puzzle. The contrast between these two interstellar visitors served as a reminder of the vast diversity of objects that likely populate the galaxy. For every familiar, readily explainable object like Borisov, there might be a Oumuamua lurking out there, a cosmic enigma pushing the boundaries of our understanding and challenging us to expand our models of the universe. The discoveries of Oumuamua and Borisov, while remarkable in their own right, have opened our eyes to the possibility that interstellar visitors might be far more common than we once thought. Our solar system, once perceived as a relatively isolated island in the vastness of space, is now understood to be part of a dynamic, interconnected cosmic web, with objects constantly exchanged between star systems. This realization has fueled a new era of astronomical exploration, with scientists eager to find and study more of these interstellar messengers. Fortunately, a new generation of powerful telescopes is coming online, promising to revolutionize our ability to detect and study faint, fast-moving objects like Oumuamua and Borisov. The Vera C. Rubin Observatory in Chile, with its massive 8.4-meter mirror and a wide-field camera capable of capturing the entire visible sky every few nights, is poised to become a game-changer in this field. Its legacy survey of space and time, set to begin operations in the mid-2020s, is expected to detect hundreds, if not thousands, of new asteroids, comets, and potentially even more interstellar objects during its 10-year mission. The prospect of discovering dozens of interstellar objects each year is incredibly exciting for astronomers. Each new object detected will offer valuable clues about the formation and evolution of planetary systems, the diversity of objects that populate the galaxy, and the potential for life beyond our own planet. By studying the composition, trajectory, and behavior of these interstellar wanderers, we can piece together a richer and more nuanced understanding of our place in the cosmos. The era of interstellar exploration has truly begun. With powerful new telescopes like the Rubin Observatory coming online, we are on the cusp of a revolution in our understanding of the vast and enigmatic realm beyond our solar system. Each new discovery has the potential to rewrite textbooks, challenge our assumptions, and inspire a new generation of scientists and explorers to unravel the mysteries of the universe. The arrival of Oumuamua and Borisov, these interstellar voyagers from distant star systems, has ignited within the scientific community a profound sense of excitement and a renewed appreciation for the interconnected nature of our universe. Each interstellar object that graces our cosmic neighborhood carries with it a wealth of information, acting as a cosmic postcard from a distant star, a time capsule carrying secrets of worlds far beyond our own. By carefully studying the composition of these interstellar travelers, we can glean insights into the building blocks of planets around other stars. The presence or absence of certain elements and molecules, the ratios of isotopes, these subtle chemical signatures can reveal a great deal about the conditions under which these objects formed, and the types of planets that might exist in their home systems. It's like receiving a sample return mission from another star system, delivered to our cosmic doorstep without the need for a decades-long spacecraft journey. Take, for instance, the hypothetical case of an interstellar object found to be rich in organic molecules, the building blocks of life as we know it. Such a discovery would be profoundly significant, hinting at the possibility that the ingredients for life are widespread throughout the galaxy, perhaps even commonplace. Similarly, analyzing the isotopic ratios of elements within these objects can provide clues about the age and evolution of their parent stars, offering a glimpse into the stellar history of our galactic neighborhood. Each new piece of information gleaned from these interstellar travelers helps paint a richer and more nuanced picture of the universe we inhabit. It allows us to place our own solar system in context, to understand whether the processes that led to the formation of our sun, our planet, and ultimately life itself, are unique or part of a grand, universal pattern. The study of interstellar objects is, in essence, a quest to understand our place in the cosmos, to unravel the story of our own existence by examining the remnants of distant worlds. The excitement surrounding Oumuamua and Borisov has spurred ambitious plans for the future of interstellar object research. No longer content with simply observing these fleeting visitors from afar, scientists are developing bold concepts for missions that could one day rendezvous with an interstellar object, study it up close, and perhaps even return samples to Earth for detailed analysis. Imagine a spacecraft dispatched to intercept an approaching interstellar object, equipped with instruments capable of analyzing its composition, mapping its surface in high resolution, and even deploying a lander to collect samples. Such a mission, while technologically challenging, is within the realm of possibility in the coming decades, and would represent a quantum leap in our understanding of these enigmatic objects. These future missions could answer questions that we can only speculate about today. Could some interstellar objects harbor evidence of extinct or even extant microbial life? Might they contain clues about the existence of advanced extraterrestrial civilizations, perhaps in the form of technological artifacts, or unusual isotopic signatures indicative of artificial processes? The possibilities, while still firmly in the realm of speculation, are tantalizing and fuel the drive for further exploration. The study of interstellar objects is still in its infancy, yet it has already revolutionized our understanding of the cosmos. As we continue to scan the skies with increasingly powerful telescopes and develop ever more ambitious missions, we are poised to unlock a treasure trove of knowledge about the universe, its origins, its evolution, and perhaps even the existence of life beyond our pale blue dot. The interstellar messengers have arrived, and we are eager to decipher their messages from distant stars. Oumuamua, the first interstellar object ever detected passing through our solar system, has left an indelible mark on the world of astronomy and beyond. Its arrival in 2017, like a message in a bottle from a distant shore, ignited a firestorm of scientific curiosity and public fascination. This strange, elongated object, tumbling through space with an unexpected acceleration, challenged our assumptions about the cosmos and pushed the boundaries of our understanding. While the debate over its exact nature continues, the prevailing theory that Oumuamua was a dark comet, a chunk of ancient radiation-altered ice with hidden outgassing, has provided a plausible explanation for its peculiar behavior. Yet, even with this explanation, Oumuamua retains an aura of mystery, a reminder of the vastness of the universe and the countless wonders it likely holds. Perhaps the most important legacy of Oumuamua is not the answers it has provided, but the questions it has inspired. Its discovery has spurred a new era of interstellar exploration, with astronomers eager to find and study more of these celestial wanderers. Powerful new telescopes are coming online, promising to reveal a hidden population of interstellar objects, each carrying a story of its own, a cosmic postcard from a distant star system. Oumuamua, the enigmatic messenger from afar, has reminded us that our solar system is not an isolated island in the vastness of space. We are part of a dynamic, interconnected cosmic web, constantly exchanging material and perhaps even life with the galaxy around us. As we peer deeper into the cosmos, with ever-increasing curiosity and ever more powerful tools, we can be sure that more surprises await, each discovery pushing us closer to unraveling the grand mysteries of the universe.